The trace function I'm not going to cover because Tomer did that in the recitations, but he did that using these slides. I mean, he did that on the board, but using these slides. I just want to remind you two things about the trace function. So you remember those things, right? If you from the recitation, I don't need those things. I need two things. First of all, I need you to know what's the definition of the trace function, in case you haven't been in the recitation or forgot. There are several ways to define it, and I'm looking for the one I like, and I don't see it. Yeah, here it is. So one way of defining the trace function, it's like a basis-independent way of doing that, is using the embeddings. So let's say that you have a L over K is a finite separable extension, and you look at some algebraic closure or normal closure. Hopefully you remember what that is, but it's not really important for me. You just need to know that if this extension is not normal, then some embeddings will take L to some other copy of it in some algebraic closure. And L hat is where all of these copies go to. But don't worry too much about it. You have a finite separable extension, and there is this nice closure of it. Then, right, you have this notion of embeddings of L over K. Right, okay. So yeah, there are several ways of doing that. I'm kind of stuck between which to say, so I'm not going to say any one of them. And if you want to define the trace of L over K with respect to this field extension of some elements in L, then what you should do is you just sum up over all of these embeddings applied to A. Okay, so that's the more convenient definition. And I should say that the only theorem I care about, there's one theorem I care about which actually appeared before, is that when L over K is not separable, which is annoying, the trace is zero. It's a zero function, it's always zero. And that's if and only if. So when the extension is separable, which is our case, the trace is not the zero function. Okay, that's all I need. And all the content you have here is a proof of that. Yeah, there's one. There's many because it's a linear map, but there is one, at least one. So that's all I need from that. The trace maps elements from L to K. Oh, maybe I should, yeah, check, okay. It maps elements from L to K. It's not going to be the zero map, and that's the formula for it. You can also cook up a formula using, once you choose a basis of L over K as a vector space, and that's what we saw here before. We chose a basis, and you can look at the trace of some metrics and so forth, but you can do it like basis independent, and that's the best way to do it.
The other way with the trace.
Yeah, same thing. Yeah, you have to take a normal closure. Yeah, that's what kind of hidden in this. Yeah, and it's hidden here because the sigmas goes out of L, outside of L. Yeah. The trace element of K. So trace goes down. So it takes element from A. It sums up, you're right, it sums up elements that potentially are not in K and are not in L even, but it's symmetric enough that it goes down to K. Yeah. It requires a proof. But Tomer did that in the recitation. And yeah, so this is the second definition I gave. The first one is like determinant of symmetrics, and the proof told you that these are the same. Yeah. But Tomer, I think, did that. Yeah. I know you don't maybe remember, so that's why I'm pointing out exactly what I need, but everything is here and more than what Tomer did. So you see, like, don't worry about it. I mean, you should look at it if you have some time, but that's all I need for what we need. So don't worry about that. So it's kind of, I just wrote it down because I didn't want to just say it, and then you have to look it up. So it's here, and you can look at it. It's also not, I mean, it's completely standard, so you can find it in different books, but every time the notations is a bit different and so forth. So here it's written maybe not in the best way, but the proof is there. What I do want to talk about are dual bases. This is, I'm going to spend some time on it. Yeah, good. So let's say that you have a finite separable extension of fields, L over K. And again, when you have that, you can think of L as a K vector space, of course, right? And because it is a K vector space, you can form the dual vector space, which, if you remember, we slightly talked about it. Maybe I didn't call it the dual, but when you talk about differentials, we talked about it. It has nothing to do with differentials, don't worry. So these are just all the homomorphisms from L to K over K, all the linear maps from L to K. I mean, that's the dual of a vector space in general. Even if you don't know that you have seen it, like many times. So let me give you an example. Let me show you how an element from L gives you such a homomorphism from L to K. Okay, just as an example. But it turns out it's going to be more than an example. It's going to be exhaustive. It's going to be all of the examples. So let's take an element from L, and I want to show you how you can get from it a map from L to K, which is K linear. And this is the map. I'm going to denote it by phi sub x. Right, so it's a map. It's in L star in this thing. And I'm going to tell you how it operates given an element from L, right, because it's a map. So phi sub x at y, where y is in L, you do the following thing. You within L, you take x times y, you just take the product, and then you trace it down to K. Right, so it's a map from L to K. It's kind of obvious it's K linear because it's a composition of two K linear maps. Right, multiplying by x is K linear. X times y1 plus y2 is x times y1 plus x times y2. And also it respects the K linearity, of course. And the trace is also K linear. I mean, multiplying by x is even L linear, but never mind. The trace is K linear. And so when you compose linear maps, you get a linear map. So this is definitely a linear map. And moreover, so I just show you an example. Like for every x in L, you can find a linear map from L to K. Take the product of your input y with the prescribed x and trace down. But what I want to say more is that when the extension is separable, and that's the assumption, for different x's you get different examples. Right? So phi sub x and phi sub x prime is different. And why is that? So this is phi sub x applied to y, and this phi sub x prime applied to y, right? Because phi sub x is just the trace like that. And if for every y these two are equal, which would mean that the two maps, phi sub x and phi sub x prime, are the same, then it means that for every y, using the additivity and so forth, the trace of their difference times y is 0. The linearity, because I put the, like, I took the subtraction of the inputs and not the.
So linearity is calculated separately.
No, it's just generally true. Separability. You know, in the 1 second. Right. Good. So we know that. That's always true. That has nothing to do with separability. But when things are separable, it's not interesting because the trace is always 0. So, but when you're separable, what we said is that this is not the 0 map as a map, like the trace function. But you see, if x is not x prime, where taking x is different than x prime, then when you go over this times y for all y in L, you're essentially going over all elements in the field. So what this says is the trace of this times, so that this trace function is always 0, which is a contradiction to the separability. Right, so because you're separable, you can't always be 0. And that can only happen if x equals x prime. So when x is not x prime, this can't happen. So it means that the phis are different. Phi of x and phi of x prime can't be the same all the time. Yeah. So, okay. So up here, I just wrote, again, the definition. Right, for every x, we have this example. And this is an example. I mean, this would be different example for x and x primes. And what I want to do now is to construct a map psi that generate examples. So from every x in L, it produces phi sub x, right, the way we did. So now I'm considering a map of like maps, of maps, because psi takes an element to a map, and no, maybe just two maps. Okay, never mind, because the phi is a trace. So anyhow, never mind. So I'm looking at this thing, the example generating, psi is the way we generated the example from every given x. And what I'm saying is that even that has a structure. It's not just a way of generating examples. It's a monomorphism of k vector spaces. So what do I mean? If you take x and x prime, and you look at the example coming from x plus x prime, so then in this thing, this function, phi sub x plus x prime, which is this thing, then that's the sum of the two examples when you take x and x prime separately. Right, so psi is linear. It's also k linear, k goes out. So I'm not writing that, I'm just writing the additivity part, but it's also like respects the k, a multiplication by k goes outside like it should. Okay, so and what I want to say is that these are all options. There are no other. So L star is completely covered by those examples. So in what sense? So this is a recall from linear algebra. I'm not sure you've actually seen it, but it's something you've seen maybe in a different language. If you have, generally speaking, a subspace and its dual, when they have the same dimension, something I'm going to use, sorry, I can do everything. And because in our case, L over K is finite dimensional, so this is also finite dimensional. And since psi is also one-to-one, this is what we showed before, x and x prime goes to different examples, then it has to be onto. Because these two have the same dimension, and it's a one-to-one map, it's a homomorphism, a one-to-one map, so it's onto. So really psi is an isomorphism as K vector spaces between L and L star. Right, so L star is always like L, it's the same thing, just like X is thought of as phi sub X, but it's the same thing. It's like the same structure in this sense. I mean, what structure do you have? Like just vector spaces, but the same structure, it's like one-to-one and onto. And from here on, I'm going to kind of identify L star with L. So I mean, L star technically, I mean, you can't multiply an element from L star with an element L. Like these are different things. But via this psi, you can kind of take an element from L star, do the inverse, do the inverse part, get an element from L, and then you can multiply them. Like the silent isomorphism, it's called. Like you don't want to kind of write it in the notation. You just know it's there. You just set up the types correctly. So I'm going to use that now. So what I'm going to do is the following. This is the important part. So if you give me now a basis of L over K as a K vector space, so here it appears that the dimension is n, then I'm going to define a basis for L star. Okay? And it's going to be called the dual basis. It's going to be the unique basis that does something. It's the dual basis for that. I don't know why I say maybe I wasn't sure of myself. But it should be the dual basis. I think I was sure. Anyhow, it's denoted by Z1 star up to Zn star. It's a sequence. It's important that it's going to be, so Z1 is going to be related to Z1 star, and Zn is going to be related to Zn star, and so forth. In what sense? In what sense this is dual? In the following sense. If you multiply Zi star by Zj, which again is very weird because they don't live in the same field, but you understand they live in the same field. This lives in L, this lives in L star, and there is the psi that can go back and forth. So you actually should apply psi inverse to that, really. Never mind. No one writes the psi inverse. If you take them, so that's an element in L now. Trace it down. You want to see 1 or 0 depending on whether or not I equals J. So it's like the identity matrix in a sense, right? You want kind of orthonormality in whatever sense. This is like an inner product, and you want orthonormality. You want this basis. You want Z1 and Z1 star to, like, the inner product should be 1, but Z1 and Z2 star should have inner product 0. It's not orthonormality, but like the same. Okay, so that's important. So let me just, if you want, you can forget all about that and just trust me that for every vector space L over K, if you give me a basis, I can associate it with another basis of L star called the dual basis, and it's defined like that. In order to prove that, the moreover requires a proof, you just need to show that you solve some linear system of equations to find the Zi star. And there is a unique solution, so it's actually the dual basis. Yeah. Questions? Yeah, you should think of it as an inner product. Yeah, that's what I said. So technically it's an L star. So there is no, like, what does this like even mean? But what I said is that whenever you see an element in L star multiplied by an element in L, you apply psi inverse, for example, to move from L star to L, take the product there. So there is the silent isomorphism between them. Yeah. But that's how it's always written. So it's not me like being lazy. It's like standard way people write it. Okay, so again, every basis every basis of some vector space, generally vector spaces, but these are just fields, extensions, like, and when you think of L as a K vector space, has a dual basis like that. Yeah, I know it's quite a lot, but with that we can do something very interesting. So first of all, let's relate the trace and all of that to what we said so far. So here is a little claim. Let's say that R, like in this picture, yeah, in this picture, let's say R, but don't worry about that. I think this is a better picture. I mean, it's the same picture, but no lines like that on purpose. So let's say R is a subdomain of L. Okay, so it's like the same thing. You have R, it's fraction field, there is a field extension, and therefore R is a subdomain of L, just a subring of L. And I'm going to assume that R is integrally closed, which again means that every element that is integral over R and which is also in K is actually in R. So R is nice. Like valuation rings are like that, right? Valuation rings are always closed in the function field. Then what I'm saying is that if you take an element in S, namely an integral element in L over R, and you trace it down using the L over K trace, there is no S over R trace. You just trace it down, it will go to R and not to some element in K. So again, when you are in a situation where you have a valuation ring, but any ring, any domain, look at the field of fractions, you extend it. So think of this as a valuation ring, the function field and some function field extension. And then this is the integral elements, the integral closure of that, which is, we know what it is. The intersection of all valuation rings containing R. Never mind that. What I'm saying is the trace will kind of respect that arrow. It won't go like that. Trace of an element in S, it can go to an element in a general element in K, but will only go to R. Trace respects integrality in that sense. At least if R is integrally closed. I mean, if R has its own issues with K, it should resolve them before moving forward. But other than that, does that. And the proof is like a three-liner. It's very simple, but just. So why is it true? So we know that sigma of X, like any K conjugate of X, so you gave me X in L, which is integrally closed. So we know that its conjugates are also integral over R, right? We said that, the same witness. And so the trace, which is just a function of those, like a function of all of those, is integral over R as well, right? It's just a function of things that are integral over R. And we know that R is integrally closed by assumption, I guess. Yeah, what is theorem 14? I forgot what it is. I have a missing piece. Sorry. Yeah. There's nothing there. I didn't know what I need anymore, and there's nothing there. Right. Good. So we know that the sum of these, which is the trace, is integral over R, but it's in K. I mean, the trace is always goes to K, but we know that it's integral over R, and since R is integrally closed, it means the trace is in R. Right. So again, you take an element X in S, namely an integral element over R. The trace of that element is just a sum of sigmas. Each of them is also integral over R, because they have the same witnessing polynomial for that. So that the trace of L over K applied to X is an integral element over R, being a sum of such elements. But the trace, generally speaking, without any relation to that, is in K. So it's in K, it's integral over R is integrally closed, so it's in R. Good. And now comes the fun part. So if you remember, we had this, if you remember, we had this theorem. I'm going to remind you in a second. I'm going to annoyingly replace every letter by another, but with some collisions. But I'm going to use that, but that's the theorem that that's the definition I want, and that's the theorem I'm proving. So what's the definition? It's not the definition, the notation. So if you have f over L, a finite separable extension of u over k, now we are in function fields, not just fields, and you take a prime, that's the first time we see it essentially, more or less. You take a prime divisor downstairs of u over k, then I'm going to denote by O prime p the integral closure of O, P, and F. So finally the story is, you have E here, F here, this is OP. So I'm going to take a valuation ring as an example of a ring which is integrally closed in E. And that's going to be, I'm going to denote this by O prime P, OP prime. That's notation. The integral closure of OP in F is denoted by O prime P. Okay, just definition. Just definition. And if you remember, we had this theorem that tells us that if you have, so you can choose if you want to read the red or the black, but let's read the black for a second. If you have, generally speaking, this picture, the integral closure of R in L was the intersection of all valuation rings that contains R. That was this theorem, right? Exactly this theorem. But if you think about it for a second, OP prime, I mean, what we said here that if you take the integral closure of OP, that theorem tells you it's precisely you should intersect all valuation rings of L that contains the thing downstairs here, OP. But if you remember, we had names for those things. And this was a finite set, by the way. This was exactly all of those O capital P's. Right? O capital P was defined to be exactly those valuation rings of L that contains OP. So really the theorem that we had, which was slightly difficult to prove, says this thing. It says that the integral closure, this is just a notation, the integral closure of OP in L, in F, is precisely the intersection of the O capital P's that we like, that sits above little p. So now we understand what integral closure means, like in this sense. An element is integrally closed, so think of it as kind of a function, right? What the things here are functions. So downstairs in OP, you have functions in like x maybe, and upstairs you have functions in x and y's. So, and saying that a function is in OP means that it's defined at OP, right? That's what it means. So when you look at this, you understand what are exactly those functions that are integral over OP. These precisely those functions that are defined at all points above little p. Because this is all functions defined at point capital P. This is the functions that are defined at all points over little p. And what I'm saying is that that's the meaning of the integral closure in our context. It's all the functions that you have the next. Now you have a y with some algebraic relation to x. And now you look at all functions, now here in the new world of x and y, that can be evaluated at every point above little p. This is precisely the integral closure. Okay? Okay, so this I'll skip, that's easy and boring. So first of all, OP, which you actually know that, but also OP prime are PIDs. They're generated by one element. And using the weak approximation theorem, you can find that element. It's slightly boring, so I'm not going to do it. But OP you know is a PID. OP prime you don't know is a PID because you just defined it, but it is a PID. Intersection of PIDs in general is not a PID, but because of the structure, it's a PID. It's kind of boring and long. But because it's a PID, so here are some facts out there. So first of all, without OP, even without OP prime, even OP is something that you know already, if you saw the videos. So if you have a prime divisor, an element in the valuation ring which has valuation run, one is called a local parameter. This is kind of the generator. Here, the way I think about it is like, so this is the way I think about it, is that every function that vanishes at p is a product. You can write it as, you can factor out 1t times maybe an element which may or may not vanish, but at least is defined at p. So it's like factoring out how many t minus p's, like x minus p's do you have, like in the expansion. Right? How many times you kind of vanish at t. That's exactly the valuation. So I'm going to skip that. That's just the same thing. But the following claim tells you that, which you're not going to prove also, it actually immediately follows from that, tells you that if you have a valuation ring with local parameter t, all of the ideals of this ring are precisely of those four. This was in the homework. Yeah. This was like all, like, yeah. But the meaning is that, every ideal is essentially obtained by, I mean, it's local. So the only thing you have is how many powers of t kind of divides you. There is no p and q. It's like there is one player here, and the whole question is how many powers of t divides you. It's like a beginning of kind of unique factorization in a sense. You factor out t's locally. But this was in the homework, yeah. So if this was in the homework, then that should have been in the homework, like all of that, like PIDness and stuff. Because this is like stronger. Yeah, but I wrote the proof here. So this claim is an addendum claim. So you don't even have to read it. So let's not read it. Not addendum proof. So don't worry about it. But what is important is this notion of local integral basis. So, okay. So again, just to recap, OP prime, the only thing I need from the last like 10 minutes is that OP prime, the integral closure of OP in L, which is like was defined very abstractly. It's actually completely non-abstract. It's precisely the intersection of O's of capital P's where capital P is over P. That's what it is. I mean, yeah. When I say that like that, so what I said is this thing, right? So when I say it like that, it sounds like I understand those, and because of that, I'm going to understand this. Like pedagogically, it's true because we learn about those before we learn about these, so this sits in your brain better than that. But actually, it's not that way. It's like two-way street. We understand this, and then we're going to understand that, and vice versa. But that's the thing that we just proved and talked about. So that's kind of the bottom line from what happened. And there's also the trace and dual basis that I'm going to do now. But that was the last 10 minutes. That's what I really needed, in case you kind of lost me. Maybe any questions before I move on? Okay. Okay, so definition. You have this field extension f over e, and what you kind of want to do is you want to understand the point. You're going to look at the point downstairs, p, little p, and you want to understand what are the p's above it, what are the e's and the f's and so forth. And for that, what you are going to do is you want to kind of choose a basis of f over e, as e vector space, which is nice with respect to that little p. Okay, so with this in mind, this is the definition. So a basis of f over e, for which this holds, I'm going to talk about it for a while, but for which you see on one side you have OP prime, on the other side you can form all kind of sums taking like the coefficients are coming from OP. OP is in little e, is in e, it's small. It's like the scalars. And these are kind of the vectors of the vector space. So OP prime, so if this happens, if everything in OP prime, if OP prime is precisely this sum, namely things you can get using scalars multiple of these basis elements by OP, right? I mean, this is a basis of E. When you form this initially, you were expected to kind of multiply them by elements of E. The scalars should have come from E. Right? That's a basis of f over E. Usually, I mean, what does it mean? It means that E times Z1 plus E times Zn is F. Like everything in F can be written as a linear combination of these I's with scalars from E. So what I'm saying here is, on the one hand, you don't have F. You have OP prime. You have a subring of F. It's this thing. On the other hand, you don't have all the power of, I mean, Zi is an element in F, but you are not allowed to use all scalars in E, just those that are in OP. And what I'm claiming is that if this happens, there is this equality. In a second, I'll tell you that one of them is obvious. But if you have this equality, then that is called an integral basis or local integral basis of O prime P over OP. The right name for it is a good basis for P. It's like a basis of F over E that works nicely with trying to understand little p. Okay, so again, the definition starts without mentioning p, and then p appears like here. But you should have in mind, let p be a place we care about, little p. And then a basis of f over e is called integral basis or local integral basis. Local because we're looking at particular p. But nice or good for p if this holds. Yeah.
Is integral in something like that. To generate like this basis.
So in a second, I think you want to say that zi's are integral or something. That's true, but
Yeah.
I'm going to digest this expression now. but just the expression itself, like this equality, when that happens, we are going. It doesn't always happen. Sometimes, I mean, the ZIs were only promised to work, like to generate everything when you have scalars coming from E, like the bigger thing, not just OP. So when you kind of look at the kind of lattice in a sense, you don't look at the entire field, just the scalars only coming from some subring, and you generate things, you don't know what you get. I mean, you get something. In a second, I'll tell you that you can't get more than that. But you get something, and turns out when you get the maximal thing that you can, which is this, well, it's not entirely correct. I'll talk about. But when you get this equality, you are happy. You'll see why. But happy means I give it a name. It's a local integral basis. Yeah. So good. So let's do that. So let's assume there is an equality. I mean, no inclusion is true in general. But let's assume that there is an equality. No, sorry. If I assume there is an equality, I kind of done, right? So let's assume that the ZIs. No, actually I was right. So let's assume it's kind of funny. So let's assume that the ZI is a local. This basis is a local integral basis. Namely, this happens. Okay. Then the first thing you can see from that is the ZIs, which potentially could come from like big F, like the big world, not necessarily O little p. They're actually coming from O prime p. I mean, if this happens, then the ZIs are coming from O prime p, because you can just use so why is Z1 in O prime p? Because you can just use 1 times Z1 plus 0 times Z2 and so forth. So you can see that Z1 is there because 1 and 0 are in OP. So if that happens, it's kind of it's not general. Nothing is generated. But if that happens, then the ZIs are in O prime p. That's obvious. But that may lead you to the false conclusion or question, maybe not false question, but that maybe that's the if and only if. So maybe if when the ZIs are in O prime p, then you get equality. And that's not true. I just want to stress that. So when the ZIs are coming from O prime p, then of course this thing is a subset or something, I don't know, of O prime p, right? Because everything here is O prime p, but it doesn't mean you get everything. Right, so saying that you have an equality implies that the ZIs are in O prime p, but saying that the ZIs are in O prime p doesn't mean you have an equality. Yes.
We assume such one doesn't exist.
Oh, we do not. It's a theorem. Good. Yeah. Good. So I kind of said it could be like a empty definition that never happens, or for some primes they don't happen. Or something. So it turns out that for every p there is a local integral basis. Actually, if you take any basis, like without p in mind, it will be an integral basis for all but finitely many p's. So like a basis is usually okay. Like generally, I mean, it's not hard to find local integral basis. I mean, it's hard not to find them. It's hard to be bad for a particular. But I'll talk about that. It appears later and I prove it also. So don't worry. I don't need that, so forget about that. Right. That's how we think about it, exactly. And what I said is that there is always a good basis for every p. For every p, there is a good basis, sorry. Right. Like every basis is good for all but finitely many p. But I think here I'm kind of, maybe I shouldn't say it, I think that no basis is good for all p's. Maybe in like weird, maybe if F is E or something, I don't know, but generally speaking, that's the case. I think, but never, we don't need that. So forget about that, don't worry about that, don't worry about that. I'm skipping things, which I'm doing the video. See, it's a lot. And last semester it happened, like always, like, no skipping. Now, the entire thing here is just in order to define the notion of a different. I'm doing a lot to give you a definition, and we are one step away from the definition. So I need to do one more thing, which looks very weird, and that's called the complementary model. So far we talk about dual basis and local integral basis, and now I'm kind of going to combine it to this notion of complementary module. Yeah, so, but essentially almost the last uphill we have, so in the course, so be with me, bear with me. So this is just repeating the definition, because if you remember we had like proofs, like 10 slides proof, so I thought you may forget things, but we didn't do the proof. So we know everything here. We know what is F, L, E, K, O, P, O, P prime. And the definition is as follows. So, and it's a weird definition when you look at it in the beginning. So, sorry about that. But the complementary module, which is something I'm defining, obviously it's going to be a module, over this ring, right? We said the modules are over rings rather than just fields. So the complementary module over OP is this weird set. What is this weird set? So you're looking at all elements in F, and you are doing this experiment. You are multiplying, in order to decide membership here, whether Z is in CP or not. You have many tests to do. It's not easy to be there. So you take any element in the integral closure of OP, you multiply it by Z. I mean, right, everything happens in F here. Trace it down to E, and check if you land in O little p. So again, there is some element here, Z, and he wants to know whether it sits in the complementary module, which is not like drawn here. It's going to be like, okay, you can draw a little bit of it. Let's talk about it for a second afterwards. So what you do in order to decide whether this Z belongs to the complementary module, you look at the product of it with every element here in O prime P, and trace it down and check if you fall to OP. Right, so this is the like a dry way of saying that. It's good. We like CP. I mean, we like that CP is. You will see. You have to, just wait a couple of slides and you'll see where I'm going. But let's say like basic things about it. First of all, like 1 is there. For example, like Z equals 1, the element 1 in the field is there, because 1 times any element in OP prime is some element in OP prime, and the trace of OP prime is OP. That was a lemma that we had with this drawing. Wow. Yeah, this one. It tells you that if this is the integral closure of that, and R is integrally closed, okay, it's fine. Evaluation rings are integrally closed. Then trace will not go like that. It will always send integral elements to the ring over which you're integral. Right. So in our case, this is OP and this is OP prime. So if you take an element for OP prime, because OP is algebraically closed, is integrally closed, the trace will map it back to OP. So that's what I'm saying. So 1. We skip most of it, so not like, so 1 satisfies that, because the trace of O prime P is OP. And actually, every element in O prime P satisfies that. Because if you plug Z, which is in O prime P, you get some element here, which is in O prime P, no matter what element you choose here. And then it will, by the same reason, trace down to OP. So we know, so in terms of pictures, okay. So we know that the complementary module is a bigger thing than that. Like that, okay? Can contain more stuff. It's bigger than the closure, yeah. We'll understand it much better in a second, but I mean, at least by definition, it's that thing. The definition is very weird, right? You wouldn't expect this definition to be useful at all, but it's a good definition. You'll see in a couple of minutes why, but that's something we know. Another thing we know is that, I mean, just, kind of to justify the name, CP is closed under addition, right? Because if Z and Z prime satisfies that, then the trace sums up nicely and so forth. So it's closed under addition, and it's also, I mean, if Z is an element in the complementary module, then Z times any element in O prime P is also there. Because if you have a Z, if this is satisfied, then Z times an element in this set just kind of swallowed to that set anyhow. I mean, it's kind of, so really these two together tells you that CP is an OP prime module, because it's closed under addition, and it satisfies the, and it kind of, there is the tchunat hablia, there is the swallowing property. So that's why you call it a module. I mean, I probably use it somewhere, but and sometimes actually we think of it as an OP module, even though it's an O prime P module. right? It's saying less because you reduce the ring, but it's also an OP module because it slows under that. In particular, it slows under if you use less scalar. But never mind. That's just basically the name. I don't really. Maybe I use it once. Now that's not a nice definition to go outside the break before you don't want to go to the break, having this definition in mind. So let's try to understand this better. So the one thing I'll use, and let's prove that I think it's good to prove it just so that you can understand these notions, is that say that you have a local integral basis of f over e for some p. There is always a p in my mind. And let's denote the elements of this basis by z1 up to zn. And I mean, saying that this is a local integral basis, I kind of reminding you here, it's exactly saying that this equality holds. That's the definition of local integral basis. I just kind of repeated it here so that you can see it. Namely, it's a basis such that you can form all of OP prime using like OP linear combinations of these elements, and those elements are from OP prime. Then what I'm claiming is that we understand exactly what is the complementary module, at least in terms of the dual basis. So the complementary module is obtained by linear combinations of the dual elements with scalars from OP.
Same object.
The Zi star. Right, so that's related to the other remark. So this is not an element in L, but in L star, but we think of it as an element in L using psi inverse. Right, there is an isomorphism between L and L star. So yeah. Right, so you have this, you have X, you go to phi of X in loop psi, yeah. You define the dual basis, you get some elements, and then you do psi inverse. But you don't, if I write it, it won't end. So you can't write psi inverse here. No one does. They just kind of L is L star. But I mean, it's from L to L star. So it can't be like technically.
This case, you take a style like it's in like the same brand.
No, I mean, so what I mean is that you gave me a basis in L. So actually here it's not L anymore, it's like F, but never mind. You gave me a basis in F. And there is this notion of a dual basis. And so you get those ZIs, stars, sorry, and they live in F star, what was L star before, but F star. And when I write things like that, I mean, I did a psi inverse to that in order to get an element in F back. Because I can't like multiply. Yeah, so you need to solve a system, it's non-explicit. So it's like maybe I can, it was a long time ago. No, after the trace, right? Yeah. Yeah. So the Zi star are obtained from the Zi by those that solve this linear system of equations. So it's very kind of non-explicit. I mean, you can do it, you can solve it, but I mean, it really depends on.
So I have a feeling that dual basis and the basis are practically the same up to side. Say no.
No. Yeah, exactly. Yeah, they're actually like orthogonal in a sense. So I mean, Z1 is orthogonal to all the Z2 star up to Zn star, and it's kind of aligned with Z1 star in a sense. In this sense, the trace of the product is 1. These are all vector spaces. Everything is our vector spaces. So it's at the level of vector spaces. Maybe I should have done some example, but yeah.
It has some basis.
We are going to see an example. Good. Yeah, we're going to see an example, like a concrete. Yeah, good. Actually, there is an example. Sorry. Yeah, here still. Yeah.
So say this side doesn't take the stuff.
No. I said that. Maybe sorry. If I said that, what I meant is that. So these are defined like solving some system of linear equation. So actually, even writing that is right because you don't have Zi star times Zj as something meaningful. So what I mean is psi inverse of Zi star times Zj. All right. Where are we? Yeah. So maybe I just state that and then let's take the break. So again, So you took I don't remember where we were. So, oh, that's the proof. That's the proof of something. Yeah, no, that's sorry. It all looks the same. You have like CPs and OPs. Okay. So if you have a local integral basis for P, namely zi of 1 up to zn satisfies this, then what I'm saying is that the complementary module is exactly that. That's what we said. And maybe if it's a one-liner. Okay, no, let's take a break. It's two-liner, but let's take a break. And it's a one-clicker. Okay, so let's prove this claim. Again, if you have a local integral basis for P, namely this, then the complementary module is that. Where again, we understand that stars are actually embedding of using psi inverse and so forth. So let's see the proof. I think it will help you appreciate the definition of the complementary module because it's a nice tool. So there are two directions, right? I want to prove under this assumption that CP is that. So I'm going to do the two inclusions. So let's start by taking an element in the complementary module. Okay. So whether it is in the complementary module or not, it's an element in F. So using the fact that this is a basis, just a basis even, of F over E, despite, it's more than a basis. Just being a basis of F over E means that you can write Z as, using these basis vectors. Namely, you can write it as xi zi star, where xi are coming from E. Right, just because this is a basis of F over E and this is an element in F. Now, if I want to prove that Z is in CP, so if I want to prove this thing, so namely that Z is here, because Z is a general element in the complementary module. So if I want to prove that Z is here, compare these two, I want to prove that the xi's are in OP. Right, because that's what I want to do. So let's just do that. Let's prove that each xi is in OP. So each xj is in OP. So let's fix an xj. And so what do we know? So we know that zj is in O prime P. Right, we know this. And I told you that you can put a 1 before zj and 0 before the other ones, and this tells you that zj is in O prime P for that particular j that you currently care about. So with zj is in O prime P, z is in the complementary module, that's the only place I'm using it. So we know that their product trace down is going to be in OP. That's the definition of the complementary module. The complementary module being here means that if you multiply me with every element in O prime P and trace down, you get something in OP. So since zj is in O prime P and z is in CP, we know that this trace is in OP by definition. But now let's look at this trace again. Forget about that. Let's just look at this trace. So this trace, well, just plug in the expansion of z using the zi stars. So this trace, right, I just replace z with the entire expression above, this one. And now I can use the fact that the trace is additive, right? So the trace can go inside the sum, and the xi goes outside of the trace. Why, by the way? It should have been inside. Right, because the xi's are in E. So because they are in E, and trace of over E is a E linear, so it goes outside like that. No, the xi's are, I want to prove that they are in OP. Right, so they are just in E at this point, but you already are in OP. But anyhow, you do get that. And now what is this thing? Exactly, so this is just 1 or 0 depending on whether or not I equals j. So this is just going to be like, all the summands are going to be killed except for I equals j, which will give you just xj. So this means that xj is this thing, but that thing is in OP from before. So xj is in OP as we wanted. Right, so that's what we wanted to do. I mean, we wrote z like that. Initially, the xi's were in E, but now they're actually in OP. We know that they're in OP. So that's one direction. So the other direction, so I'm going backwards actually, I'm going to take, it's easier I think, I'm taking something here and I want to prove it's here. And membership in CP is, just need to show that trace of me, like the candidate, times any element in O prime P is mapped to OP. But there is a condition to be checked. And so you just check the condition. So again, let's prove this thing. So in order to prove that, I need to take an element here in this set that I want to prove is here. And any element in O prime P, so I'm going to call it Z prime, so that we kind of remember it's in O prime P. And I want to show that the trace of the product is in OP. That's the definition of membership for Z to be in the complementary. Okay. So let's see. So Z is an element here. This is the candidate, right? It's a member here. So I can write it as sum of xi zi star, where the xi's are in OP. Z prime is an element in O prime P. And if you remember, the assumption was that O prime P is also a sum like that. So I can write Z prime as also using the ZJs with coefficients also in O prime P, in OP. I mean, both the xi's and the yj's are in OP, but for different reasons. But then that's it. The trace of the product, well, you just take the product, you get this double sum. The double sum goes out of the trace. The xi's and yj's now are actually in OP, in particular in E, so they go outside the trace. And when you look at it for a second, the only thing that survives is when I equals j. So you get a sum of xi, yi, which is in OP because all of them are in OP. And that's what we wanted to show. Just by definitions. Okay. Yeah. So what we just showed, and we're going to use it now, is that if a local integral basis allows you to understand to write down nicely the complementary module. And what I really want to show you is this. It's a claim, but it's actually maybe should be a theorem. So for every small p, actually the complementary module and the integral closure of OP are very much related, and it's this thing. So for every little p, you can write the complementary module. So I told you it's kind of bigger than O prime p, but you can always write it as some element. I'm going to talk about the meaning of that element, but some element, not uniquely element, but some element times O prime p. That element is usually not going to be in O prime p. It's going to be a function that's not defined in all. I mean, O prime p is this intersection of. Let me write this here. It's here, but okay. O prime p, if you remember, is the intersection of OP over going over all big p's over little p. And so TP is generally, I mean, sometimes, typically not, but sometimes it can be the case that TP is not in O prime p. Namely, it's a function that's not defined everywhere in all those capital P's. But what I'm saying is that the complementary module is not much larger in a sense than O prime p. If you know algebraic number theory, it's called a fractional ideal. It's like an ideal. It's like you take this and you divide it by something. Like, I think of 1 over TP in my head, but don't worry about it. Just, the complementary module is just some product. It's just some element times O prime p, and that element is going to be very important. It will encode the information you want, really. No, that's a good question. So, like, size-wise, it's the same, like a cardinality or something, but TP could be like, it could have poles at some capital P above little p. Right, yeah, and that's the difference between the complementary module and O prime p.
Cardinality doesn't make sense because
Right, it's all the same, yeah, right.
It has more points.
It has, right, and it's actually exactly that. I mean, you're required to have those poles also. Okay, so, but we'll talk about it, but let's see the proof. I think it's a helpful proof to see. Right, exactly. And then the question is, who cares about CP, of course? But you'll see. I mean, I'm introducing another object I don't care about and then tell you it's very related to the object you do care about. Yeah, we'll see. But anyhow, let's see. So first of all, theorem 24, which I skipped, but that was related to your question, guarantees that there is always a basis which is a local integral basis. For any particular little p, there is always a local integral basis for it. So you should trust me, it's not trivial, but it's going to be in the addendum videos. It's of the same spirit of what we're doing, so I decided to skip it. And claim 26, which we just proved, means that once you have that, then we know how to write the complementary module using the dual basis. Right, so when you have equality here, you have equality here.
So it's always a basis, and you just use it.
Right, there is always a basis, and I'm using it in that I'm using its dual to span over OP like CP. Yeah. Or generate, it's the right word in this context, but as a module. And I don't want to say generate as an OP module because if you have many words, it will confuse you. Generate, like that. You can use ZI star with scalars from OP and to sum them up and to get everything in CP. And only that. So, okay, but I want to cook up a TP. That's all nice. I want to find a TP that satisfies that. So the way I'm going to do it is I'm going to use the weak approximation theorem, which I did some statistics. It's the #1 used theorem in the course. So you use that. So what we are going to do is we are going to find an x in E, at the bottom, whose little piece valuation is at least, that sounds weird, but you will see in a second why, the negation of, I'm going over all capital P's above little p, and I'm going over all, there is something here moving, move away. And I can't, you like algebra? I'm not going to do that. Okay, just see there. When I move the slide, maybe it'll go away. So now I want this valuation to be larger than that for all capital P's and for all functions. These are functions, right? For all functions in F. Finitely many. There is a finite number of places above little p. Right. And of course, only n zi's, stars. So you can do that, just, there is some number here, and I just want to make sure. I don't care about any other place. Just that little p be larger than that largest number. It's an easy instantiation of the weak approximation. The weak approximation allows us to do much more than that.
In F.
Right. In F above little p, yes. So I just wrote down it again. So that's what we know. That's how we chose x. And now let's see. Let's see what, x is an element at the bottom, at E, but let's see what's the P valuation, capital P valuation for some capital P of x, which we just found. X is kind of clearing denominators in a sense. You'll see what I mean, but of x times zi star. So I'm taking a capital P, I'm taking one of those zi stars, and I'm looking at this valuation for a second. So of course the valuation of the product is the sum of the valuations, and because x is in E at the bottom, instead of writing V capital P of x, I'm writing that. Right, I'm doing the ramification index and multiply by V small p of x. But by our choice, and because E is at least 1, of course, so this is at least 1, so you can ignore it. So by our choice, you know that this is non-negative, because we know that this plus that is non-negative. Yeah.
So you just can take x to be like the highest valuations you want.
Exactly. And some other place is going to get false because of that. But that's fine.
Just make it the highest.
Right.
It's like the LCM.
I don't know. Yeah. So it's like taking, if you want, say if p was 0, then it's say I'm going to multiply by x to some high enough power. But of course, x may have pole, it has 1 at infinity. So someone pays for that. But at that particular place you care about, you're fine. And the weak approximation does that simultaneously to many places together. Right. Someone else, yeah. And the strong approximation tells you you can make sure only one place will pay for everything. But never mind. Yeah. It's a lot. But anyhow, we know that. So we know that in our language, x times zi star is defined at capital P. And for every capital P and for every I, right? Because we made sure x will satisfy that for all of them. So this means that x times zi star for every I is in this intersection, because it's in each of these OP of capital P's, which, if you remember, is just the integral closure of OP.
Quantities, because we said that the integral closure of some,
Ah.
I think, module, I think it was.
This one?
Yeah, the integral closure is like the intersection of every.
Right. All the evaluation rings above you that contains you. Exactly. And here, that's kind of the picture that's here. So we have that. Okay, so I mean, I need to give you a TP, but I'm kind of slowly constructing it. So at least we have this xzi stars in O prime P. And if you remember, CP was that. I mean, the assumption was, so the way we started it, we started here, we used the theorem, the claim that we proved to show that CP can be expressed in terms of the dual basis. So I kind of just reminded you of that now. So this is just that. CP can be written as OP combinations of the dual basis. So x times CP, if I multiply everything here by x, and I kind of pushing x here if you don't mind, then you see x times zi star for every I is in OP prime. And therefore, this whole thing is in OP prime. So to summarize, there exists an x in E such that x times CP is in O prime P. That's what we just did. X was coming from E, if you remember, and we just proved that. And the way you should think about it before moving on is that CP may have like functions with poles and stuff. I mean, this is no poles. All functions here are defined on every point around above little p. Here it may not be the case, but I kind of clear the denominator in some sense. I multiply by some x, and now that's fine. So you think, right? So here you have functions that are defined that every prime divisor above little p. Here maybe not, but I kind of lifted it up. I multiplied by, so all functions here can be multiplied by the same common function in E in such a way that now all functions that are defined. That's called clear denominators, if you think about it. Okay, anyhow, so we have that. And now we should recall that CP is an O prime P module. I said that at the beginning when I justified the name of a module. And also x times CP is an OP module, right? I mean, x times something plus something is x times something plus, everything is preserved. It's actually, yeah, it's an O prime P module, but x times CP is in O prime P. That's what we said here. So again, CP is an O prime P module. X times CP, what I want to talk about, is also an O prime P module, but it's an O prime P module that sits inside the ring over which it is a module. So it's an ideal. That's what we said. Like a module over a ring that sits in the ring has to be an ideal. So really what we figure out here is that x times CP is an ideal of O prime P. So that's why it's called fractional ideal, because you need to multiply by something to be an ideal. So when you divide by x, it's like you get it back, but it's not an ideal, but it's you can write it as a function.
Finite x is in TP. What is the difference between
You want TP now. One second.
why didn't we finish?
Because it's not equality. I want to find, yeah, good. I want to,
Maybe n to be too large.
exactly. But at least you know it's an ideal. So this T that kind of generates CP out of O prime P, it doesn't have zeros. It's like, it's not redundant. All the zeros are in OP prime already. So let's see. So we know that O prime P is in CP. Yeah, I mean, right. So actually that's kind of the proof, but we know that's something we immediately saw when we talked about the complementary module. But I mean, what is CP? Just this T times O prime P for that particular T that you kind of decided to use. So this means that if you kind of divide by T, it's like 1 over T times every element here is an element here, right? But that's it, right? So 1 over T is here because you can choose 1 here. So 1 over T is here. Namely, it is in the intersection of all capital primes, all capital P's. So this means that 1 over T has a non-negative valuations at each place here. So T has non-positive ones. So it's 1 over, it's a minus. Yeah. The important thing is this claim. I'm getting to a definition. Like all of this is to get to a definition, not all of this, but I mean, it's particularly required to get to the definition. So let's say, so what I'm saying here is that, there is a freedom in choosing T that generates CP from O prime P, but that freedom is completely determined once I know the evaluations of this T at capital P's above P. So what do I mean? So let's say that T is one such generator. Well, what I'm saying is that for every capital P, that's equivalent to saying that for every capital P above little p, the valuation of T and T prime are the same. Right, so if you gave me two representatives, what I'm saying, if T satisfies that and also T prime satisfies that, then they have the same valuations at capital P's, and that's the only case in which they both satisfy that. So really the entry ticket in order to be a generator of CP is to have the right valuations at capital P's. Okay, so really these valuations, the numbers are what matters, not the particular identity of the element.
It's actually not a parameter, but in
Like many capital places.
not one.
Yeah, something like that, yeah. But with negatives also. Because local parameter has valuation 1, and this is like these are negative valuations all the time.
No, it's a local parameter with CPU.
Uh,
It's a unique parameter.
It's a parameter, yeah. So no, but it's not local parameter in any.
Fine. Characters what is CP.
Yeah, but look, it's a parameter, yeah. But not it's a different name, it's a different thing. Yeah. Okay, this is kind of obvious, but let's do it. Just definition. So forget about that for a second. Generally speaking, if you have two functions T and T prime, and you consider and you have this thing. So namely for every capital P above little p, the valuation is non-negative, then that's exactly like saying that T over T prime is the intersection of the O capital P's, right? Because valuation is non-negative, which is precisely the valuation integral closure of the OP, which is the same thing as saying the T times O prime P is contained in T prime times O prime P, just by multiplying by T prime, and then multiplying by O prime P. So that's true, and I think I copied it here. Okay, so to say this is to say that. To say that T over T prime has non-negative valuations above little p is to say this inequality holds, or inclusion holds. And so to say that they have the same, to say this, which is what was in the statement, to say that T and T prime has the same valuations that every prime divisor above little p, well, it's of course the same thing as saying that the valuation of the ratio is 0 of those places. And using that in both sides of inclusion, it's the same as saying that these two are the same. Right? This is contained in that, and that's contained in this. And that's CP. So since everything is equivalent here, I'm really saying that T prime generates CP if and only if it has the same valuation as some other generator. And this claim I'm not going to prove, but I just say that I didn't mean to prove it. It just says that I need that. I need the statement, and it says that CP is usually actually O prime P. Like generally, you don't need to clear denominators. Like for most little p's, you get the same thing. Right. Exactly. Finally, many weird points in which something happens. Yeah. Interesting. Yeah. I mean, if you want to know someone, you need to know its misbehaviors. Right? That's like in life. Take it like. Yeah, and it's also interesting. But yeah, so you'll see. That I'm getting to the definition. That's an important theorem. It's only 2 slides of proof. Oh, 3, but I'm not going to do it. I'm going to record it, but not do it here. It's very simple. But I think I don't know if you would expect it or not expect it. I'm not sure what's the intuition. I mean, you have right now. It should be like empty set at this point. But it's true. And that's it.